Hi there, welcome to our video describing the Java Essential Dynamics Inspector software. Whether you're running experiments in a lab or creating simulations on a computer, collecting data and choosing the right methods to analyze that data with is an important part of the scientific process. We wanted to simplify data analysis with JEDi. In this video, we will describe how it works, the pipeline for running JEDi, and some of its features. For specific information, you can use the chapter markers in the video description or on the YouTube player to skip to the section that you're looking for. JEDi contains many tools to really trick out your analysis with once you know what you're doing. This includes things like kernel PCA, free energy surface computations, and much more. The steps in this video are meant to get you started, but for a full list of features, be sure to check out our user's manual, which can be found on our GitHub, which is linked to in the video description. The purpose of JEDi was to simplify the analysis of protein structure and dynamics. All you need to get started is some protein structure data in the standard PDB format, as well as a JEDi parameters input file, which is read by the software. With JEDi, you can generate protein dynamics analysis remotely in a computing cluster or even right on your local computer. After taking in your data, JEDi will analyze the protein's motions and try to filter out the unimportant ones using PCA. The remaining motions are considered the essential dynamics of the protein. Essential dynamics helps explain protein function. For example, one motion might describe a conformational change that activates the protein. JEDi can not only find this motion, but also visualize it. For protein structure data, each eigenvector is interpreted as a global motion, meaning one motion of the protein. The associated eigenvalue is the size of this motion. Each component of the eigenvector can be used to score how much each individual atom contributes to the motions, enabling researchers to identify where on a protein structure a specific motion is taking place. JEDi reads in the standard PDB format. So to get started, you will need some protein structure data, which can be obtained with whatever experimental or computational method you have access to. I have some molecular dynamics simulation data, so I'll be using that for this video. Protein structure data files can get pretty large, so it is sometimes nice to be able to run analysis somewhere other than your personal computer. JEDi has your back, as it can either be run remotely on a high-performance computing cluster or directly on a computer. Generally, if the data is more than a few gigabytes, you probably want to use a cluster. Since JEDi was written in Java, the program can run in any environment that has Java version 1.8 or higher. Once you have this, you're good to go. The parameters to run JEDi are in a single input file, rather than a set of command line prompts. If we open the file JEDi parameters.txt, we can see that each parameter for defining your JEDi run is a key value pair. You can use these to personalize your JEDi pipeline. Now, all you have to do is feed this file with all the parameters into JEDi for it to begin processing your data. Maybe grab a snack or read one of the thousands of papers in your stack while you're waiting for it to finish. Let's take a deeper look into running JEDi. The JEDi parameter file organizes the parameters into sections. There are a lot of parameters, and most of them let advanced users control every aspect of the analysis. In this video, we'll be going over the main 4 sections that you'll need to get started. First, we have 3 global parameters that need to be set for every run. The first parameter here, directory, tells JEDi where it is on your system, and the path you provide is the root directory from where JEDi will begin to search for all your files. Second is description, which is used by JEDi to name output files and directories. Lastly is the reference PDB. This is the structure that will be used to align all of your data. Often, the first structure in a trajectory is chosen, but choosing your reference is arbitrary. However, it is critical that you keep the reference constant for all parts of your analysis. Having the same reference allows you to compare your PCA results between different experiments. To simplify this, I like to put my reference structure into a separate directory away from the data and point this key to it. JEDi is run in two stages, a pre-processing stage where it reads in your structures and an analysis stage where it performs your customized PCA analyses. Both of these stages are controlled by the same parameter file. Pre-processing simply loads and formats data but does not perform any analysis. When you run pre-processing, JEDi will read in all PDB files in the root directory and output a formatted, aligned matrix file for the analysis step to use. After this, you no longer need the raw PDB files. After pre-processing, you can start analyzing the trajectory. JEDi can create a lot of output, so to keep it all organized, JEDi uses the description parameter to create a unique output directory. You can run different PCA models at the same time to get a complete look at your data. JEDi will create a thread pool and assign one thread to each analysis to accelerate the overall process. JEDi will create a unique subdirectory for each analysis. The analysis parameters begin with the original PDB coordinates key, which tells JEDi where to find the coordinates file. You can set this path to the matrix created during pre-processing, or to another trajectory matrix, such as one outputted by JEDi's pooling driver, JEDi's subroutine for combining two or more trajectories. Now that we've discussed what JEDi does and how to use it, let's get into the good stuff, its features. A focus of JEDi, so important that we included it in the name, is the inspector. JEDi outputs many high-quality PNG files so that inspecting your data is easy. Most of the figures and PyMol visualization used in this video are direct outputs of JEDi. PCA is a powerful tool, but one of its weaknesses is its sensitivity to outliers. By inspecting JEDi's pre-processing statistics, you can identify outliers in your data. JEDi can correct for outliers using the doOutlierProcessing key. Here, you can specify a criteria for defining outliers through either a z-score or a MAD score, or mean absolute deviation. JEDi performs both outlier removal and outlier selection, and then compares the results. Outlier removal helps the essential motions capture the dominant global modes, instead of a motion just due to outlier atoms. For this, the positions of outlier atoms are replaced with their mean value. Outlier selection can be useful to check things like the quality of your data or to find rare events. Next, we have to consider what resolution to analyze the enzyme's motions at. JEDi offers support for alpha carbon, backbone, heavy atom, and all atom resolution. A residue subset can be chosen for each resolution analysis. Usually, the smaller your subset, the higher the resolution you can have without risking too much noise in the resulting motions. For example, you may want to run alpha carbon on the whole protein, backbone on some secondary structure regions, and then all atom on only the active site residues. Creating a targeted funnel with your data like this is a great way of saving on computation time, as all atom PCA on large atom sets can get to be pretty lengthy calculations. Typical alpha carbon PCA on a moderately sized protein could take anywhere from a few minutes to a few hours, depending on how much data you have, and the equivalent all atom PCA could take days. That is, it would take a long time if it weren't for JEDi's new Hierarchical PCA method, HPCA. HPCA uses a hierarchical approach to perform an all-atom PCA computation on a large subset at a fraction of the time. It works by computing the essential dynamics of each residue individually, convoluting them all together, and then recomputing the overall essential dynamics. So now, after deciding what to analyze, we must now decide how. In JEDi, you can construct essential dynamics from a covariance matrix, correlation matrix, or a partial correlation matrix, each identifying different types of motions. For example, covariance is the most common model because it finds the largest motions a protein undergoes, which often drive conformational change and functional activities. Correlation helps find the most correlated motions between residues, which can be especially useful when functional motions are not the largest. You can run the correlation or partial correlation matrix by turning their keys on. JEDi will always run the covariance matrix by default. Finally, JEDi provides you with one more quality control for your essential dynamics analysis: model sparsification. Users can choose a threshold value for the correlation and partial correlation models. In the model matrix, any value less than the threshold is set to 0, so that only the correlations above the set threshold contribute to the analysis. This decreases the effect of non-essential motions on the results. Typically, correlation thresholds above 0.5 and partial correlation thresholds above 0.1 are considered conservative. They're a good starting place, but you might have to play with the thresholds to get the best results for your data. Here, we can see the effect of increasing the correlation threshold. The thresholding removes the background wiggles, drawing our attention to the motions of interest. This is essentially everything we need to run JEDi. Now you can just submit the parameter file like we did for the pre-processing, and you can walk away until the program is done. The steps presented here represent the minimum that JEDi is capable of. There are plenty of advanced parameters and post-processing analyses, such as free energy surface calculations, kernel PCA, mode visualization, and much more. JEDi also comes with a subspace analysis driver, which allows you to compare the essential dynamics between multiple proteins. And JEDi can also perform PCA on distance pairs between atoms and residues. For more details on the capabilities of JEDi, as well as a deeper dive into the algorithms used, check out our paper and our user's manual on GitHub, which is linked to in the video description. No matter what kind of motions you're after, JEDi gives you the tools to find what you're looking for. Happy analyzing, and may the force be with you.